So today we're talking about quadcopters. This is kind of a presentation about quadcopters and how mine works. It was a senior design project. My name is Tom McCardle. These are a few quadcopters here, none of which are mine. Mine is right here. As you can see, I designed my own electronic speed controllers, abbreviated as ESC, and currently right now you can see that the green light is on, it's disarmed, so we can go ahead and play with it all we want, touch it, whatever. You can see the small ESCs right here, or Hobby King ESCs. I have two of those on there to increase reliability of flight. And then mine, you can see, are right here. They're a little bit larger. They're my first version of the PCB. On here, on top of there, you can see the H-bridge driver. The MOSFETs were not getting enough voltage to turn them on, so I needed to increase the voltage and decrease noise on the circuit. The H-bridge drivers basically fixed everything. And to test everything, I use a GUI made by MultiWii. Currently I'm using a flight controller made by MultiWii. It's the MultiWii Mega, and it's using the Mega 2560. It currently has a plug-and-play GPS with it, along with a Spectro AR610 receiver, and I'm using the respective DX5E transmitter, and I have a 3-cell lithium polymer battery. Sorry for the bad camera action. I'm going to go ahead and I'm plugging that in. So I have about 12 volts hooked up to it. You can hear the Hobby King ESCs making noise. Recognizes that it's a 3-cell battery. And here's a small demonstration. You can see the light, the green light, disappear. That means that it's armed. You can arm it and disarm it with the transmitter. So down and left, arms it, disarm, and you can also see on here when it's armed and disarmed, the little light where it says level should appear and disappear. And so when it's armed, increase throttle, you can see all motors turn on and they spin. I currently have a slower ramp up function on my ESC, so they do not ramp up as fast. I currently have it tied to this box so it will not lift off and fly away and break. You can see here that there's 6 GPSs, if this will focus. There's 6 GPS satellites that it's connected to. It can also sense the level. The leveling, just same as an airplane. There's also a compass that it's attached to it, and it shows which devices are being used, which sensors. So it has the accelerometer, barometer, magnetometer, and the GPS. And right above there, you can get real-time data based on the accelerometer, gyroscope, magnetometer. And currently we're looking at the real-time data for, well, we'll go ahead and disarm it. And so now we're looking at the real-time data for the accelerometer and the gyroscope. And so when I move it around, you can see the data coming in, kind of moving around up and down. I'm just kind of pushing it up and down. And so when we jump over here to my code, well, we can go through a little bit of this presentation. The way that the flight pattern is set up, I currently have a plus setup, and so this, let's go ahead and focus that. And So we'll go ahead and just use this guy as my pointer. So D3 and D2 are both spinning in the same direction, and so D5 and D6 are spinning in the opposite direction. And so if you wanted the yaw to spin the copter in this direction in a clockwise manner, you would turn on or increase the throttle on D2 and D3. And if you wanted to spin in the opposite direction, you would spin or increase throttle on D5 and D6 and decrease D2 and D3. And if you wanted to move forward, decrease D2 and increase D3, and kind of the same thing for D5 and D6 for turning left and right. Here's some engineering requirements. I wanted to at least carry 6.7 ounces, which is the weight of a GoPro, and I wanted to basically be able to reach the speed of a boat for when you're wakeboarding, so I can film myself. And here's the block diagram. This is just a very basic block diagram of the overall system, and we'll go ahead and kind of jump through to a little bit of the code. This is for the motor driver, the ESC. So the ESC has the flight controller coming into it. It has the MOSFET driver and the motor driver, and then the motor. So the MOSFET driver is basically the microcontroller, and the microcontroller on my ESC is an Amiga 2560, and that controls which MOSFETs to turn on. And as you can see in this picture, it's a little bit vague, but if you look right here, you can see right here you can see that there are 6 MOSFETs, and it controls each phase. And so there are 3 phases, and so in order to turn on one phase, you would turn on A high and B low, and that would allow current to flow into the motor through phase A and out of the motor through phase B. And there are 6 different commutations, so you turn on A high, B low, C high, A low, and so forth through the 6 commutations. And whenever you have A high, B low on, you would check on phase C to check for the back EMF, which gets into closed loop circuit, which if we go into the programming side of things, which I don't have it in this slide, so if we go into the programming side of things, you have basically 6 different phases that it could be in. It could be in stopped, it could be aligning, braking, ramp up, open loop, or closed loop. Usually when it's ramping up, in most cases, when it's ramping up, it's in an open loop. And what the difference is between the two are basically the open loop controls the speed of the motor just by saying, hey, I want to go this speed, and so it always stays at this speed. And the closed loop uses the feedback of the motor to actually control the speed of the motor. So the zero crossing is always in the center location. Sorry, I'm jumping around quite a bit, but so if there are 3 phases, and we're looking at phase A, we'll turn on phase A and we'll turn off phase A, or we'll turn on A high, and then within the commutations, A high, then we'll turn off A completely, and then we'll turn on A low. As you can see here, maybe this will be easier to see. So we'll turn on A high, B low, and then B low, C high, and then C high, A low. So you see on that second commutation that A was completely turned off. So A was just completely floating. So if we were to look back here, it would be, this will be a position where we'll have A high, B low, and then B low, C high. And so at that position, we'll be checking A high, or phase A, for zero crossing. And so once it crosses that specific point, we'll be checking the ADC, the phase A ADC right here. And once it crosses VCC divided by 2, or as we have this voltage divider, it's set for about 200 or 2.5 volts. And so once we get about 2.5 volts, then, well, actually this was set up for originally 7.4 volts, so it's different now, but half of that voltage will indicate a zero crossing. And so whenever it crosses half that voltage, it'll be at this location, and that's at the point where you would want to set or end a timer. You start the timer at the beginning of the commutation, and you end a timer at the zero crossing, and then you double that time, and that will determine your commutation. And that's basically how you do the closed loop. So if we jump back over here, a few more things about the GUI. You can see the real-time output of the transmitter. So as we increase or decrease the transmitter, we can see it right on the output there. And if I were to arm it, so there it's disarmed, now it's armed, and now I can see the real-time data on the output right here of what each motor is actually getting. So that is the actual output of what each motor is getting. And we'll go ahead and disarm it. And then we can click over here to the map and actually look at the GPS. We're currently getting 7 satellites right now. So if we go over here and we jump to the tab where it says map, we'll get an actual GPS coordinate of our exact location. So I'm showing everybody where I'm at. And this is this actual software is not used to set the waypoints, but Multiweave Pirate, I believe you can actually set up waypoints and such. So there you can actually see exactly where we're at. If I were to spin the quadcopter, you can see the angle actually spin on the screen. And if you scoot over here a little bit, it looks like it tries to center on the quadcopter, so we'd actually have to zoom out, but you can see Salisbury Street, Fowler. So it is actually in a very accurate location, and in this apartment complex it is actually in my exact location, so it is a very accurate GPS system.